So let's start. So this presentation about IoT protocols. I'm Antonio. This is Jaime. We're from relayr. I would just like to know how many people here have worked with IoT protocols, and I'm talking something different from HTTP or WebSockets. How many people here have worked with protocols like Mqtt or CoAP? Okay, few persons, okay. And how many people heard about these protocols, although they never worked with it? Okay, a few more. Okay, so we're going to focus very much on Mqtt and CoAP. The other ones is protocols that have been around for some time, HTTP and WebSockets. And we're going also to show you something which you as a software engineer, and this is mostly a software engineers and software developers conference, usually don't see, which is industrial devices. And it's a totally different world from the world you are used to when you work in software. So remember to use the app to rate the session and also to ask questions. And we're going to go really fast, okay? This is the first thing. So where this all started. So this is the original paper that for the internet from Licklider, where they were thinking about creating this network that would connect, that would be able to share information using computers. So the computer used as a communication device. This is in 1962, the original paper, then another paper in 1968, and this here you have the evolution of the Arpanet. So in the beginning it was just something in the West Coast, then later the West Coast to the US connected to the East Coast, and then you start having other types of networks and more networks connected. So, but we already have a lot of internet protocols. Why do we need more internet protocols? This is the issue. Well, because first we're going to have a totally different order of magnitude in terms of the number of connected devices. Right now, in the beginning, you had just, as you see in that slide about the Arpanet, with just hundreds, thousands. When you had the mobile phones, you start having a couple of billions. But now we're going to have much more than this. And this is some projections from the MIT Technology Review. And this is the number of devices that will join the internet. So, and this is projections from multiple companies. Some are research companies, others software and hardware companies. So Bosch says that by 2020, there'll be 14 billion connected devices, Cisco 50 billion, Gartner, it's a research company, they say there will be 309 billion in supplier revenue. The economic value added will be 1.9 trillion, and another research company, IDC, says there will be 7.1 trillion. So there's a lot of revenue to be had there. And on the other hand, what we see is a different trend, which is the cost of hardware is going down. So right now, you can buy things extremely cheap, like this? Like this. So this is a device that is manufactured in China. It's called ESP8266. This thing costs $2.5 yeah, you can buy it. Yeah, exactly.
Board with a chip is about like $4.
As a microcontroller, as a Wi-Fi chip. It can work even as an access point. The first thing that you need to be careful with is you buy this thing from Chinese manufacturers, developed by a Chinese company, is when they put the FCC logo there to say it's certified, it's really not certified. So if you want to develop an industrial product with this, we had this experience in our company, be really careful. This is good as a prototyping thing, but if you want to really make an industrial strength product that you want to have on the market that needs to be certified, maybe you should think twice, okay? And maybe use a more common manufacturer like TI or any other of those manufacturers. But this is the type of thing. This is already very cheap, and you can do a lot of things. As GPIOs, as a very rudimentary analog to digital converter. It has a USB to TTL adapter, and it has also power supply. So you just power it from your USB. Yeah. You can also use a battery. There's a battery shield. There's a lot of stuff.
80 megahertz, actually.
Yeah, exactly.
It's pretty, I mean, it's powerful enough to run most of the things.
Yeah, this is a couple of years old. They have a new one now called the ESP32. This one, the ESP32, has also Bluetooth, and it has also some crypto capabilities, so you can encrypt the flash. You can have the boot be secure, right? Secure the bootloader. The question is, right now the software stack is very behind, so unless you want to work with the stuff that Expressive, which is the company that manufactures this, puts out there, which is C, which is RTOS stuff, you have to wait a little bit more, or you just have to code it yourself. But this is an example of a very cheap device that you can have, so that really confirms this trend. So what's a constrained device? Okay, so constrained device, what type of constraints do they have? One, they have limited processing power, so they don't have a lot of CPU power. They cannot do very expensive computations. And they have also limited memory. So you see this thing here as a couple of megabytes. You don't have a lot of memory. You cannot store a lot of data, and you cannot do really complex crypto. For instance, right now the support for TLS there. If you want to do Mqtt, we're going to talk about this later. Mqtt TLS. Not all Cypher suites are supported, and it's kind of sketchy, the support for there.
It's a hack.
Yeah, it's kind of a hack. So if you want to connect to AWS IoT, for example, it's really not the nicest of things. Yeah, it's not official, it's not the nicest of things. Also, the networking. Networking, it's really heavy, and it was developed for big machines, right? For clients that are quite powerful, and for servers. So when you run on this type of devices, the network is also unreliable. Imagine that this is powered from batteries, and the battery runs out. And now there's no network. There's something that was sending data in a network, and now it's no longer there. So the networking is unreliable, and also you want to use low power. So for example, there's a radio standard developed by a company called Sigfox, and it's a thing that works in the ISM band, so 833 megahertz here in Europe, 915 in the US. And this thing uses very low power, has a very low data rate. You cannot send a lot of messages. I don't know the number by heart, a lot of messages per minute. But this can be used, for instance, for detecting leakage in water pipes. So what you want to do, you have to dig up something on the street and put the leakage detector there, and you want this to last for a long time. So you cannot drain a lot of power. So you have to, having this requirement of using low power is really important, and this makes it it's one of the big constraints you have. So these three types of constraints is the constraints you have when you work in the IoT. Of course, Raspberry Pi is also an IoT device. It's a constrained device if you compare it with a server, but if you compare it with this leakage detector sensor, it's much more powerful. Also, it drains much more power. So the internet, what is the internet? Well, basically, it's a network that connects different types of networks. This was the beginning. There was Arpanet, there was Bitnet, and the internet connected these different types of networks. So now you will bring other things into your internet. And this is what you're going to talk about. So one of the things here is industrial protocol. So there's a thing that has been existing for years and years, 50 years almost, which is operational technology, which is used in factories, right? So you have industrial automation, and then industrial automation started initially with things that were operated manually. Then they put some smarter relays, and they went from there and started adding computers. But this is something that developed totally separated from the IT world and the IP world, something totally separated. But now with the Internet of Things, you want to bring these things into the Internet, right? So you want to have all these interconnected. So these new type of networks will be here. So this is for the factory. If you work in buildings, you have even other types of protocols. So I imagine this building uses a system like this, a building management system that uses this kind of protocol. So these protocols were generally developed by a particular company, and then the other manufacturers started using it, so it is compatible, and so they made some standards. Some of the specs are proprietary, some are kind of proprietary. You have to pay to have access to them. But this is how this industry developed. So mostly closed, while the internet and IP is mostly open because it was a research project at the beginning. So there's one very important thing with the Internet of Things, which is that in the beginning, in the beginning of the internet, there was not a big difference between what was a client and what was a server in terms of the capabilities. But then as things progress, we see now with the mobile phones that the client has much less capabilities than the server. With the Internet of Things, the edge computing, the edge is back in the game. So edge is extremely important. And you will see that the cloud is still important, but the most important thing will happen at the edge. So imagine if you want to control some machine in a factory. What you want to be able to control this machine in a factory is to have a quick response times, right? If it's a press and you want to stop the press because there was a problem, you want to do that quickly. You cannot have the luxury of sending a message to a cloud somewhere and have the round trip time, okay? All the round trip time until you get a response in order to act on this machine. This has to be done immediately, as quickly as possible. So latency is a very important issue, which means that you have to do a lot of computation on the edge. And in fact, most of the computation will be done on the edge of Internet of Things. And the cloud will still play a role. For instance, if you have a machine learning model, that you can only run on big machines because it's very computationally intensive, you will run it on the cloud. But you want to use the results of this model in some downloadable way and then run it on the edge, because this will implement, for instance, your control loop for controlling this machine, like the mechanical press or the hydraulic press. So there are devices that are on the edge, and then there's a gateway. If you want to connect to the cloud, you have this gateway. And this gateway, basically, it's what establishes a connection, from the term, to different type of networks, which is the edge network, which could be, for instance, in your factory, and the cloud. And this gateway can be many things, from a simple Raspberry Pi, or even a device like this can act as a gateway, because using the Wi-Fi, you can connect directly to the internet. Of course, you will have to live with the latency you will have there. Or if you have a 3G or 4G or GSM, whatever, you will have to live with that latency. So a gateway is defined by this aspect of being able to connect to different type of networks. But this gateway can be a rack of servers. Okay? It can be your own local center that you have in your factory that can do a lot of computation and intensive tasks also. So there's really no one-size-fits-all in terms of the gateway. Depends on the type of application you have and how comfortable are you with your data traveling across public networks. Mm-hmm. So devices are not gateways, and this is the main thing. It's like devices talk to other devices, okay? Northbound, and southbound. Gateways talk to the cloud, northbound, and they talk to other devices, southbound. So unfortunately, I had an accident when I was coming to Amsterdam. Someone stole my backpack with my laptop, and so I cannot do this demo here. So this is a kind of, this is a device from a company called Zolertia, and this is a very low power device, and it uses a standard from IEEE. It's called 802.15.4. It was developed for low power radios. And what happens is this, you can run IP here, but the packets are really small. They're 127 bytes. So and this is IPv6, so you have to fragment that. So what the IETF, the Internet Engineering Task Force, did is they develop a standard which allows you to run an adapt IP here on these devices. So what you need to have, if you want to connect to a normal IP network, you need to have what they call the border router, which is in the border of this specific 6-LoWPAN network, which has its own specific things, and the normal IP network. So the border router will act as a gateway, because it will connect these two types of devices. Of course, you can run this as a device in the end, connected to a sensor, and then you can run this also as a border router. We'll talk a little bit more about the role these things can play when we go to CoAP. So you can have device to device, D2D, and you can have device to cloud, and you can also have cloud to cloud. So the first protocol we're going to talk about is probably the most popular one. It has been used for a long time. And in the beginning, the Internet of Things was quite powerful devices. So most of the stuff was device to cloud. And we'll see that the Mqtt is particularly useful in that regard. So it's a PubSub protocol. There's a standard. So it was initially developed by IBM, some home automation project. But then later, they opened the protocol, they open sourced it, and now it's maintained by the Eclipse Foundation. It's a small code footprint. It can work well in constrained environments. It's data agnostic. It's one of the things that Mqtt has here is that there's no way for you, when you send a message, to know which type of data is inside. Mm-hmm. So the client and the server have to be in agreement ahead of time what type of data is being shared. It's not like HTTP where you send, okay, this is JSON, or this is XML, or this is text. You send this content description, content type in the header. Here you don't have that. So it's then out of band in terms of the protocol. So this is how it works. So there's a broker there, there's publishers, and there's subscribers. So it's a PubSub protocol. And the broker manages the interaction between the publishers and the subscribers. Okay? So what it has readings and it has commands. Readings is, for instance, telemetry data from a sensor. And commands could be something to change the sampling frequency of the sensor or to control a machine like the hydraulic press I talked about. So you already see that this thing here is a problem, which is why I think this protocol is not really well suited if you want to work in a more generic IoT network. device to device, because it has the broker. The broker is quite heavy in terms of, so you cannot run it, for instance, on this device or on that one there. The broker is quite heavy, so which requires some computational power, and also this uses TCP. So the networking is kind of demanding for this type of thing. It uses TCP, so the broker is also a single point of failure. If the broker is down, nothing will work. So this is all the messages you have here. Very simple, as you see. It's a very simple protocol. You can go, if you can look in the status. There's a lot of information online about this. See what type of messages you have. So it's a pretty simple protocol. So what you do, you publish something to a topic. You define the topic. What is a topic? It's some sort of data. It's some sort of organization of my data, which I'm interested in. So here, what you have here is, for instance, something which is publishing to this topic 1, and in fact is a temperature value, okay? It's value temperature. I will talk a little bit more later about this QoS, quality of service and retaining. So this is an example of publishing a message. So what you have here, you can organize the topics in multiple ways, usually 2 ways to organize the topics. You can organize semantically, that we have here, which means that it's kind of a directory file system structure or a URL structure if you want, where you organize, it says here, I want to get the telemetry data on my house from the ground floor on the kitchen and give me the temperature. This is semantic because you look here and you can see exactly what this means in terms of the data you're getting, okay? You can also have a type of organization that is called logical. Of course, you see the problem here, this doesn't scale. If you have thousands of devices, you're going to run out of names for these things. So you can have something, naming scheme are used, for instance, a UUID. And this is called logical. You just have a device that has a UUID, 128 thing, and you just use that to identify your device. And there you don't really care, just have a mapping that says how does your device, what does your data corresponds to this device with this UUID. So also it has wildcards, as you can see here. This is a 1-level wildcard, which means give me all the temperatures on the ground floor, or you can have a multi-level wildcard to give me all the telemetry data on the ground floor, which means not only temperature, can be temperature, could be pressure, could be humidity, whatever you want to have there. You're measuring there. So there's quality of services here. Initially, it was just quality of service 0, and this means fire and forget. Although it's TCP, it means fire and forget. TCP is just a way for the broker and the client. They keep changing an acknowledgement to know that the client is still there and the broker is still there. So with 0 means that there's no state, okay? There's no state. The client sends, the publisher sends, the temperature is 32.5. The broker says, I got it. But if for some reason this value doesn't reach the subscriber that is interested in this, imagine it's something with the temperature, it's air conditioning in a room. So you want to know the temperature so it can act on the temperature on the room through the air conditioning. So if there was some problem in the network, the subscriber, the publisher publishes the temperature, but then the air conditioning would never, which is the subscriber, would never get this value, okay? With quality of service 1, you guarantee that the message is delivered. There's some state now. The message is delivered. It may be delivered multiple times. With quality of service 2, you guarantee that the message is delivered exactly once. So, and this is the last revision 3.3.1 of the standard where they introduced this this quality of service 2. Another interesting thing it has is a last will and testament. What this means is if your temperature sensor is going to die, when it connects to the broker, it says, if something happens to me, please send this message as my last will and testament to all the subscribers that are receiving my data, that are interested in my data. So this is what a last will and message means. Another thing also that it's not here, it is a retain. And this means a retain means that there is a value. If you ever work with AWS IoT, they have a thing called a device shadow. A retain is an implementation, is a thing of device shadow. It's a value. It says it's a flag that is set by the client, by the publisher, to the broker, and it says, if any subscriber, new subscriber connects to you and wants to get my data, please send them this value immediately, okay? Imagine that you read the temperature only every hour. But you publish the temperature now, but in 15 minutes, you're going to have an air conditioner that is going to connect to the broker and says, tell me what's the temperature in the room. Of course, the publisher, the temperature hasn't published any new value, but since it was marked as a retain, the value that was there before, it will be immediately sent to the air conditioning, and he can do something with this value. So there's Mqtt.org, which is like the canonical site for this kind of protocol. This is the recommended implementation in C, Mosquito. All this is managed by the Eclipse Foundation. There's another one for Java. There are in multiple languages. RabbitMQ also supports Mqtt. So this is C. If you want to use Java, there's Paho. There's a lot of good tutorials. So it's a pretty standard protocol. There's a lot of use cases out there. People with a lot of experience have used it. Okay.
Demo, tiny demo. For
okay.
Mqtt.
Now we're going to have a small demo.
More time. So just really quick, guys. I'm gonna run an app here that basically acts as an Mqtt client, and then we'll see how the messages are coming first to the broker, and then they are aggregated in a platform. So sorry, I'm gonna go back. Oh shit. All right. So if my device is online, yes, there it is. So all right. You can see that's actually my phone, and all these messages are coming, as you can see. For example, I'm gonna try to, you can see the luminosity there. So if I tap it, it will probably go to 0 to real low. Now you can see it, the luminosity values over there, 17, that tiny widget over there. And then basically, the messages are, basically the client is publishing, as you can see. Not sure if it's big enough. But you can see here how the packets or messages are coming, and this is basically
this is the accelerometer, right?
Correct.
That the phone has. That's how the phone is capable of rotating the images when you put it on the horizontal.
And this is actually pretty fast for Mqtt. Because I don't think this is publishing like 5 times per second. It's actually I don't think the protocol was actually designed for really fast publishing.
Yeah, but this app has a warning that says if you use the accelerometer sensor, if you make it publish to the cloud, it will run out your battery really fast. Because
Probably,
it's sending a lot of
exactly,
data.
sending a lot of data. But
Because you move the phone a lot.
Now the network crash or something. But you get the point.
Yeah.
Right.
Also, you could send commands. Can you try to make it play or turn on the flashlight?
Let's see. Yeah, you should be able to. Yeah, exactly. Because now we're publishing, but there it is. So my phone responds to the.
Yeah.
Oh, you can make it sound, but it's off. Obviously, right? Now you can click. Oh, you don't know how to use a Mac, man.
No.
These nerds. No, just basically no. It will not sound because it's off.
Yeah.
But you can turn the flashlight off.
Yeah.
So yeah. It's basically this, but this device has to be listening to those commands. So if this device, if a message is received from the broker and this device has no clue what's going on, nothing will happen. So the command is actually run here.
So it's acting both as a publisher, sending the data that you get from the sensors that are on the phone, like accelerometer and the luminosity sensor, and as a
subscriber.
As a subscriber, it's getting the commands from the client that is running here on the. This is the web client that is running here on the cloud. And it's getting the commands and say, turn on the light, turn off the light, play a sound, vibrate. So it's acting both as a publisher and a subscriber, which means that any device can have these two roles.
Cool.
Okay, let's go to CoAP then. So CoAP is constrained, short for Constrained Application Protocol. And the idea was, there's a lot of people out there, software developers, that know how to use HTTP. Why not try to bring all this big success, running success that was HTTP in the world of Internet of Things. So that was the thinking behind specifying CoAP, defining CoAP as a new protocol. So CoAP's Constrained Application Protocol. So it's kind of a lightweight HTTP. Okay, so it doesn't use TCP, it uses EDP. So there's the reliability in terms of the messaging is done at the application, at the protocol application layer. It's no longer done below at the transport layer. So you have to do this yourself. But it uses the same principles as HTTP. It's a RESTful interface, all these kind of things. It was developed for manipulating resources in constrained networks. Also, HTTP, it was developed kind of organically. There's a lot of things that were never put there. One of them, now with HTTP 2, was brought into focus again is the synchronous messaging, right? Well, CoAP is a synchronous messaging since the beginning, as we will see. So here, also another thing is that since this is supposed to work to be in the same type of line in terms of protocols as HTTP, in the standard, there is a specification for a proxy between CoAP and HTTP. So in the cloud, usually you have HTTP, things talking HTTP among themselves and talking HTTP to the proxy. And this translation is transparent. Okay? This translation between CoAP and HTTP transparent. So of course, it's a binary protocol, CoAP. It's not text like the HTTP 1.1. There's not as much headers as there are possibilities of having headers as you have in HTTP, but the proxy does this translation in a transparent way. You don't have to do anything. So this is the normal HTTP request. This is TCP three-way handshake. Please give me the value of this light resource. The server responds OK, 200 OK, status code. We also have status codes here, but since the messages are smaller, the status codes are also different. It's 405, usually, the value that corresponds to 200 in HTTP. And then you get the response, and you get the termination message from TCP. So how does it work with CoAP when you have an HTTP client on one side that goes to a proxy, and you have the CoAP server on the other side? So is this something you will see is that CoAP has one very interesting feature, which is there is no big difference between running a server or running a client, which didn't happen with Mqtt, where the server is the broker, and it's quite heavy from a computational point of view, and with CoAP, that's not the case. It's really, really very lightweight. In fact, you can run it on this device, okay, or even on this device if they had an implementation for it that was not half broken, like they have right now. But with this device, you can have an implementation that is really good, using an embedded operating system called Contiki, and you can run this as a server. And you will see what's interested in it. So here, what it does, it gets a request, get me the value of the light. The proxy translates this, talks to the server that is running here. It sends this, so this, you see, 205, it's the value corresponds to 200 in HTTP. And it returns here, in this case, as a XML, which is not the best of formats. You will see there's specific formats were developed by the IETF for CoAP. And it goes there, then it returns the value. And also you can have caching. This is another very important thing. Mqtt has no caching, but since HTTP has caching, and it's quite good, the way it works, since CoAP is just kind of HTTP for constrained devices, all the caching is, you also have it here. All the caching you have HTTP, all the strategies, you can have it here also, okay? Mm-hmm. So this is a very interesting aspect. And you have here, just to see, have an idea about the order of magnitude of the objects that are involved. So here is in the cloud, you have HTTP object, okay? And you can have here this implementation, the security at the socket layer, top of the socket layer here. You have an HTTP TLS. Here you have a thing called DTLS, which means datagram TLS, okay? So, for instance, these implementations, they are lacking. So for instance, Contiki doesn't have a good implementation for the TLS. There's some other implementations, some other operating systems. There's a new one called RiotOS, which is still very new, so not a lot of chips are supporting, and this has a better support for the TLS. So that's how you do datagram TLS. You can do security here, of course, on top of IP, and you have CoAP, and you have the object there. And this is in the proxy, and this is a device that is on the connected to the, for instance, get telemetry data from the sensor. You have here this thing here, so tens of bytes, hundreds of bytes, and here thousands of bytes. Just have an idea of the size of the messages. So what do we have? Resources are specified by a URI. You have get, post, put, delete, all the verbs you're used to in HTTP. You have content type support, you have XML, you have JSON, and you have this new thing called CBOR, which is concise binary object representation. So if you ever heard of a serialization format called message pack, CBOR is about as compact as message pack. It's just that the encoder, the codec, the encoder and decoder are easier to code, much shorter, so much more amenable to run in constrained devices. But basically, it's the same thing. It's a binary format. It has multicast support. This is really important. Why? Well, if you have an Mqtt, there's no multicast. Okay? So if I imagine these lights here are running as an Mqtt client. They're subscribing to some broker that is going to publish something, and you press a button on the switch on the wall, and it turns on and off the lights. Which means that each light will have to run the subscription client, right? So there's no way that I can send a single message and all these things will get notified at the same time. If you have multicast, a single message can be sent, when a particular interface can be sent to multiple devices at the same time. So for lighting, CoAP is really interesting because you just need to send a message. You can turn on and off the lights with a single message. There's a synchronous message exchanges. This is really important because imagine that the device, for instance, has a problem with the networking or the battery or something happened because it's unreliable devices. So you are not obliged to get the message immediately. Also, usually you run this in sort of low power cycles, where you turn off the device for most of the time. You just wake it up in specified times and you send a message. So it can be that my server makes a request, but the device is off, so I can't get the immediate value. Either I have it cached on a proxy on the gateway, or I have to wait. I'll get the message the response later. It's also designed to be extensible like HTTP. So here's an example of a request response, typical like HTTP. There's the temperature here. I want to get the client says to the server, give me the temperature, and it sends the value of the temperature. So this is the frame, how it looks like. So I don't go into very particular details. You can check the RFCs. They are there. There's also some books around it already published. There's a couple of implementations. I'll give you a site where you can go and you can get all the information about CoAP. So there's one thing here, which is this. There's a message ID. So each message has a message ID, which is a thing that is increased incrementally, where you can do the you can associate a request with a response, and there's this token. In this token, it's what allows you to have asynchronous responses, because this token, when you make a request but you don't get immediate reply, there's this token, so that when you get a reply, this token is sent back on the reply, on the response, and you can say, okay, this is the response to this request I made some time ago. Right? So this is the new thing here that you don't have in HTTP. So this is a confirmable message. It means please confirm that I got the response back. So this is piggyback. This means once I get the acknowledgement, I also get the response. Or it can be separate. I make the request. The server says, yeah, I got your response. I will send it to you once I have it, and you have it here. Then the client says, okay, I got the response. Thank you. This is a confirmable message. So what you have here is non-confirmable. This is just fire and forget. It's usually UDP. So all the reliability that is done here is done at the application layer. This is UDP, no TCP. There's no guarantee the message will be delivered. So you have here, you just make non-confirmable. This is a flag that is sent on the packet. Non-confirmable, and I get here the reply. And here I get the same type of non-confirmable, but I get an acknowledgement also from the client that I got the response from the server. So you can also reset. Okay, you can also reset this so that when the client makes a request, there's some crash on the client, then the server can send the message. You reset it and starts from scratch. Sends a reply and you reset it and starts from scratch the messaging sequencing, request response sequencing. So the message reliability is handled at the application layer, so it's UDP. If you make a request and you're going to have to reply, there's a mechanism, some rudimentary mechanism for congestion control, so that you cannot pile on making requests until you get the response. So there's an exponential increase up to a maximum of 247 seconds. If you can't get a response after 247 seconds, it means that you're never going to get it. They are doing better congestion controls mechanism, and much more developed than this simple one. And if your speed is your goal, you just want to go as fast as possible, you can just disable all these features. So yeah, so this is the question about reliability that you have here. So I make a connection, I couldn't get the response, there's a timeout, and now increases the time, I make a new connection, I make a new request, and I get the response. So after they define CoAP, which basically was like HTTP, but adapted for constrained devices, they said, okay, there's things that are missing here, which is like a pub-sub kind of thing we would like to have. Otherwise, are we going to compete and sell this to people that are now using Mqtt and say, hey, use this, because they say, okay, but you don't have a pub-sub mechanism. So they added something, a new RFC later, 2 years after the initial standard was published, and RFC was published for CoAP, they added this thing called the observer pattern. And the observer pattern is kind of a pub-sub, okay? So what matters is that this device here can work as a server. And there are clients that can connect to this device and say, hey, I'm interested, imagine this is reading a temperature. I'm interested in this temperature value. Wherever you want, wherever you have an update, please send it to me. So this is how the observer pattern works. So let's see exactly how that goes. Here's an example. This is from the RFC. So what the first thing it does, this is marked as an observe. There's a header there. There's an option that you send on a packet that says, this is an observer. Make a request and say, I'm interested in getting the temperature values. When you have updates, please send it to me. So it registers here on the server. So remember, this device now is a server, and the client is somewhere outside, can be even on the cloud, going through the proxy, using HTTP, translating into CoAP, and goes into the sensor network. So it goes here, and here, this is the value. And you see the observer, this thing here keeps incrementing to say, this is different values that I'm getting. Could be, for instance, the seconds that have elapsed, or the minutes that have elapsed since you make this initial request. So you get here, I'm interested in this value, I make a special GET request, marking this an observe, and I get the values updated as this moves along, and as the values change, and the server keeps sending the data. So this is a very interesting thing. As you can see, you have here basically the same thing that Mqtt provides, but without having the need to have this broker thing running. In fact, the server is so lightweight, you can run it in very constrained devices. So this was added to the CoAP spec later. Another thing, it can have block transfers. So if you have a very big response, you can split it, and then it can be reassembled at the other end. Also, one of the things I realized is that UDP is interesting, and it's really adequate for constrained devices. But sometimes you connect it to networks, like in a factory. So the industrial internet, we'll talk about this. EtherCAT, what it is basically TCP over Ethernet. So you would like to have something that talks TCP because it will be easier to integrate into this type of network. So right now they are drafting CoAP over TCP, which when people say, yeah, but you're kind of doing HTTP. They say, no, it's still CoAP. It's just that they have to adapt because there's situations you find out there on the field. Also, they're working on authentication and authorization. So the crypto capabilities of these devices are really limited. So which means that this thing on the edge will be devices that have multiple roles. You will have an authentication and authorization server that will be, when you need to access some resources, you will make a request there, and this will tell you if you can access the request, you can access that resource or no. And the same way they were inspired by the HTTP to define CoAP, they're also using the ideas that behind OAuth and the JSON Web Token translated into the world of constrained devices. So this is a place you can go to get everything about CoAP, all the implementations. You can even play with it. There's a Firefox extension that you can install, and this allows you to make CoAP URL requests. And basically, the only difference between CoAP and HTTP is that it has CoAP :/ instead of having HTTP : / or CoAP-S if it's CoAP with the TLS. So it's very interesting. You can play with it. There's a couple of test servers that have like the reference implementations, and you can see how it works with observer patterns, split messages with the block part, splitting the messages in blocks, etc. So now some demo about something totally different.
So intermission. So, okay guys, so obviously, I mean the protocols were like, right, Mqtt, CoAP, then HTTP, and WebSockets, but we're not gonna talk too much about the HTTP because actually, you probably had enough in your life. So, but what's funny is that lots of these protocols, actually including HTTP, they got into industry already, which makes it really interesting because for instance, I'm a field guy, I'm an electronics guy. I study with PLCs and all these devices like wiring, It's more like for you would be like more like an electrician probably. And the thing is that, you always had to use like really heavy tools like this TIA software in Siemens, only runs in Windows, and then, you have like...
and the protocols are totally closed, like Siemens has their own PLC.
Correct, there's SIMATIC, there's TES7, so it's quite obscure, actually.
Yeah, there is a C++ C implementation, some guy that reverse engineered it, just using a packet sniffer. That's how he did it.
With Wireshark.
But it's not guaranteed by Siemens. It might work, it might not work, you're on your own. They don't care.
So yeah, that's pretty normal in industry. I mean, like, really, I mean, this Windows 95 no, it was Windows XP for submarines or something. Anyway, like it's used in, and yeah, in industry you have things like from the 70s running. So anyway, we'll add some pictures later, but first of all, what's a field bus? Antonio showed you guys this picture before. So here, basically, in industry, we talk about protocols, we talk about field buses, and we talk about industrial Ethernet. So what's a field bus? A field bus is an industrial digital bus used for real-time distributed control. Mainly used in manufacturing, so almost all devices that we find in a factory, in the shop floor, are connected with field buses. Connects instruments, namely sensors, actuators as well, and have different topologies. So this is actually pretty like, state-of-the-art industry. So normally it was all serial and stuff like that. So controllers were connected via serial. So imagine the cable salads. And the field bus solves that. So, and it's really cost-effective because one thing you want to do in industry is to save money, of course. So yeah, there are different standards. We're gonna explain some of them really quickly. Probably you heard about Modbus. RTU is a serial. It's freaking old, like from 1979. So it's pretty cool. Modbus is returning now. I'm gonna make a quick demo with Modbus, transferring Modbus from Modbus to HTTP, actually. Usually we use Modbus TCP, which is over Ethernet. But there are others, like Profibus, it's also serial. It's like another field bus. Profinet, which is actually an Ethernet standard. Then you have CAN, which is the one on the, I think the first keynote yesterday was, they explained how they hacked the CAN bus, right, on the car. So there are different standards in a car, like there's CAN, there's LIN, there's a port that if you lift the ashtray, you will find a nice port, that you can connect an OBD device there, which is a device that basically sniffs all the data from the CAN. And yeah, you can actually have like a connected car like for less than $200, actually, with a cellular module. So, all right, I'm gonna go really fast. So anyway, EtherCAT, DeviceNet, blah, blah, BACnet. All right, that's a normal PLC. A PLC is a programmable logic controller. These things, you find them in factories. The PLC is actually that thing with the screen only. The other things are the input and output modules. And these things perform really basic functions, like turn the pump on when that sensor is released. Do this when this happens. Do that every 10 minutes, stuff like that. And now we have PFCs, which is a programmable field bus controller. So basically, they support different field buses. So all these protocols we talked before, they support them all. They're expandable. They have input and output modules that you can buy, and you can slide them and build your own custom system. And now they run an operating system. So that means that you can run Linux in most of these devices. I will show you this later, but anyway. And the thing is that manufacturers give SDKs in different languages, so you don't need to use these basically software suites that they were really heavy. And more and more of these devices have HTTP APIs. So this device that we're going to show later, this is IP67, which means it's a really high protection range. You can basically throw this from a 7th floor. Will be OK. You can spill water. You can do heavy stuff with that. And it has an HTTP API. So you can pull data from the sensors via HTTP. So it's really interesting for software developers, I think. And they have web servers, so you can ping that device. You can go to the IP address of that device, and it will open a website that you can configure and change stuff with no programming skills. And yeah, basically, that's a PFC. That's an SD card slot. You can even create your own custom image, like we did already with Yocto, for instance, and install it there. They have different network interfaces, anyway, different like input and output modules, 3G connectivity, everything. So I'd like to talk really quickly about IO-Link. I'm going to prepare the demo already. This is an IO-Link device. This is interesting for you guys because this is the state of the art in automation, actually. So these sensors have an important thing. I mean, you can read the rest of the specs. I'm going to go really fast. They have a descriptive file. So that means that when this sensor is kaput, when this sensor is dead, you can just change it. And once the sensor is dead, you just push a descriptive file from a remote server. And the file will arrive to the sensor, and the sensor will get the calibration. And if you connect new sensors in these ports, the sensors will authenticate themselves. So the sensors will say, hey, I am a temperature sensor, my manufacturer is this, and my mom is that. And basically, the sensor will start sending data immediately. So it's pretty amazing. They're not cheap. They're like $200 each. This is like 200, 300, something like that. But that's cheap, actually, industrially. That's affordable. So that's an example of a topology. As you can see, that's the computer we talked before, the PFC, the Programmable Field Bus Controller. Then you can have a server that is pulling the data because someone from the managers, they want to know what's going on the shop floor. And then you have your IO-Link devices. Or the sensors can be sending data directly to the PFC because there are modules that understand IO-Link. That's another example of an IO-Link master in our office, actually. And that thing talks HTTP, Modbus, which is really old, and Ethernet IP, which is another protocol. And you can see those slots with the screws. You have to wire the sensors. This is really, those USB things, no, that doesn't exist. You really have to wire it. So, so I'm gonna, some subtle product placement, of course. So if Antonio helps me out here, just holds this thing. So I'm gonna connect this thing, and I'm gonna show you guys how easy it is actually to use the built-in HTTP API. So first of all, I'm gonna try if the sensor replies me, because this body, okay, this body has an IP address because I know it. And no, so let me configure this, sorry. Shit happens, it's a live demo. So let me just reconfigure this. This is all good, this is all good, yes. So, all right. Yeah, there it is. So this device is replying, basically, to my requests. The only thing I'm gonna do is to run a super simple Python script that I'm going to show you later, that it will be converting, you can see here, the Python script. And you can see that it's actually making a request on this device, HTTP request. So I'm not doing any industrial magic or whatever. And that's it, just pulling a value, which is going to be, you can see here on the request, that we're actually request GDP, so get process data. And I'm going to request the index 0. All this is specified in this file I told you before, in the IODD file. By the way, we don't manufacture hardware, so I'm not selling you anything. So I'm just going to run that simple Python script. I have it here. Yes, I think it's this one. And basically, yeah, it's freaking hot here, as you can see. So, so basically, I'm pushing and reading the values. Antonio is actually touching the sensor now.
With the temperature is increasing, yeah.
And the temperature should be increasing. I have the device over here. Sorry, GOTO Amsterdam. Here it is. So there it is. That's my temperature. Just let me open this. Temperature. Yes, so that's my sensor sending data. You can probably, yeah, there it is. You can probably even, and that's the real-time data of the sensor. And I'm not doing any magic. I'm just like connecting this via Ethernet. That's it. It's powered and everything. So yeah, I like to, if time allows.
Yeah.
Maybe, well.
Another demo in the end.
Yeah, okay. We're going to do something. We're going to keep going,
yeah.
And then we will try to make a demo privately for the rest.
Yeah, I'll go just 5 minutes to this really quick.
Cool.
Just to show you, like I show you things that are currently in use, I'm going to show a little bit of a glimpse into the future. So up until now, we have host-centric networking, right? So in the beginning, the problem was how can one host reach another host? And this was all the thing that was behind the development of IP. But now, more and more, what you're interested in data. We want to abstract all the rest because the host and the connectivity is already there. So we're just interested in the data. And this is a new type of networking called information-centric networking, as you can see there. Oh.
The mouse. Move the mouse away.
No, want to make it full screen.
That's it.
Okay. So information-centric networking. So as you can see here, what's important is the data that is transferred. And there are things that are interested, subscribers that are interested in a particular data. And what is important is the type of data. I'm interested in a particular type of data, and I just want this data to get through me. And this data exists in this space, in a data space, global data space here. So host-centric networking, there's a conversation between hosts. Information-centric networking spreads data objects. It's not who you want to talk to, it's what you're going to say. So there's a standard that's been used for a long time in industry, especially in the Department of Defense, defense industries like avionics, industries for airplanes, airplane manufacturers use this, Airbus, Boeing, they use this, has been around. This is quite heavy. It's like a proprietary kind of thing. They made it like a standard, but there's not a lot of free software implementations out there. It's a very close thing. It's done for people, developed by people that are defense contractors. They say this can be used in constrained devices. But right now, you can use it just right away. It's something that was an evolved from something that existed a long time ago called CORBA. So it's just a way to exchange these objects in messages. You can see I'm not going to go into details. This is an older thing. So this is DDS in a nutshell. So there's all these kind of entities that you can see. There's anycasting and there's multicasting. And if you remember, there's already one thing that CoAP doesn't have. CoAP doesn't have anycasting. And here is ICN. And ICN is a newer thing which improves upon DDS. There's consumers. There's a certain interest. Data have a name. And the consumer says, I'm interested in this data with this name. And this is the new thing that is coming up. There's some implementation. This is basically a research project. So there's a communications between consumers and name data. There's forwarders. So it uses some ideas from the internet, like how to forward data. There's some problems still open problems to solve, like routing, congestion control. Right now, it's a polling thing only. There's no event. So for instance, with the observer pattern, you have an event-based model. When there's a change, please notify the clients that are interested in this value with the new updates. There's multiple research projects in US and Europe, and watch this space. This is really interesting. It's something that is really promising. Could simplify a lot of stuff. There's a lot of complexity they have now in all this networking because you have this host-centric networking. So, in a nutshell, MQTT, device to cloud or cloud to cloud. CoAP, device to device. This is what you need to use. HTTP1, cloud to cloud. HTTP2, we haven't talked about it. Possibly, you can use it device to cloud, okay? Because HTTP2 has nice things like a header compression. So if your device can support a crypto stack, which allows you to have TLS, then yes, please, HTTP2. DDS, cloud to cloud and device to cloud, this would be quite a powerful device. They claim they can be used device to device, but the device, it's not really a very constrained device. WebSockets, cloud to cloud. So operational technology, this will be around. You have to deal with it. It's not going to change. Then people are not going to throw out this. It's been for you. It's very expensive. It's really reliable. And there's no silver bullet. So this is us. If you want, this presentation is there. And questions.